Welcome to the examples videos. I'm going to show you 3 of them. We'll start off with more generic ones here, and then later after this, go check out the bonus example that I have add on, because those are the little bit weird ones. Anyway, let's go. Electric potential. If at this point you still can't remember, please know the definition. It helps if you know W equals QV from your old, what you call that, AS definitions. It helps. So work done per unit charge, bringing a point from infinity to a point. I must also add that it helps that you mention it's a positive test charge. So work done per unit charge, bringing a positive test charge. Because by convention, we look at how positive test charges work. So that's why it's good to mention also positive test charge. From where? This is where the second mark usually comes in. From very far away, infinity to a point. So this is what we call electric potential. How much work you need to do to bring it in. Okay, 2 marks. One is work done per unit positive test charge, blah, blah, blah. This whole thing. Second one's talking about infinity to a point. So usually it goes like this. M1 up there, A1 the second one. Please go and memorize your definitions. It's 3 marks. Then we come to this beautiful diagram. Oh my. If you haven't tried out this question, I highly recommend you do it, because then it'll be more meaningful for you, because you're like, oh my goodness, what is happening? Okay, so the isolated solid metal sphere, when you see the word sphere, they are talking about Gaussian charge conductors, where the charge, whether it's positive or negative, will probably collect at the surface. So like the one we looked at just now in the theory video. So it's positively charged, so it's going to look something like this. Variation of potential is shown. There you go, a very nice inverse law. But what do they want us to do? Use the figure to suggest why the radius cannot be greater than 1. Why the radius cannot be greater than 1? Look at this part. If you remember how we draw all those graphs just now, inside the sphere, the potential is the same. So if this, let's say, if the radius was here, then inside there it should be straight. And this will be 1. If the radius, okay, this I say label here, this radius, if the radius is more than 1 cm, then it should be a straight line somewhere, then only here go down. But it's not, it stops there. So the radius probably will be less than 1. Okay, it could, the graph can still continue, I don't care, but they're asking why cannot be less than 1. No? So we need to explain the inside of the sphere. So how we can do that? We can say, inside the sphere, let's talk about inside the sphere. So we can say things like, inside the sphere, what should the potential be? Constant. Flat, straight line. So you can say V is constant. See, we got constant here. You at 1, you're already curving down already. So of course, radius have to be less than that. So I think this is all you need to say. And you already get a B1 mark. Okay, so remember how to talk about this thing. The next one, let's scroll up there. Use a graph to show that the charge on the sphere behave as if it were a point charge. So that means when we drew this little sphere right here, you can have electric field, right? And the electric field actually looks like an electric field of a point charge, like this. But they're asking you, use the figure to show that it's a point charge. Wow. What's the equation for point charge? Can you remember? So for point charges, okay, charge on sphere behaves as point charge. If you want to use the graph of V against X potential, what is the potential of a point charge? Let's say a point charge here with some charge Q. If you want to measure potential, you need to calculate V equals to K, which is about 1 over 4 pi E naught. Let me just write the whole thing out. Times Q, the charge, over R or X. How far are you from the charge? Let's say I'm over here at distance X. Okay, this is the equation we use for point charge lah. But this one is a sphere. How can we prove that it behaves like a point charge? This is where you kind of have to use your paper 3 skills a little bit. Show that this relationship is true. What's the relationship? V is proportional to 1 over X. So they're saying, if your graph follow this equation, that means it behaves like a point charge. But does the graph follow that relationship or not? You say, yeah, curve like that, lor. Not convincing. This is 3 marks, guys. Gotta be a little bit more convincing than that. So how do you know that this is the relationship that is shown on the graph? This is where you gotta do some Paper 3 stuff from AS. So if this is the relationship, it means V equals to some constant over X. We know what the constants are lah. Q over 4 pi E naught. So that means Vx equals to some constant, which is, in our case, I just call it K lah. Okay, so let me just write this here, constant. So if you can prove that all along the graph, this is true, that means it behaves like a point charge. It follows the same relationship as V proportional to 1 over X. So the first thing I'm going to write down here is that Vx is going to be a constant K, which is a constant lah. So what should I do? Take two values of K and compare. Sounds familiar, right? So I need to calculate 2 points on the graph, 2 sets of data. You know what? I really like this first point up here. So I'm going to take this as my K, use this to calculate K1. And I'm going to use the other end. It's better to take them far apart. And I'm going to use this to calculate my second K. If the relationship is correct, K1 and K2 should be the same. So, what's this reading? This is 180. I think this is 1 cm. Yep, 1 cm. So this point is 0.01 and 180 volts. Down here is what? What's the coordinate of this thing? Is at 9, so 0.09 and 20, I think. Yeah, 20. Okay, so I take these 2 points, 2 sets of data, calculate 2 values of K, and then compare. So, right working law, because 3 marks ma. Okay, so my K1 will be V times X, which will be 180 times what I wrote just now, 0.01. This should give me a value of 1.8. Then I do my second value of K. This will be 20 volts times 0.09 cm. This one is also 1.8. Oh, very good. So, that's all. Hey, conclusion. 3 marks. Please don't forget. So, use your skills from paper 3 and draw a similar conclusion. So, since, we don't know what the mark scheme wants. So, we write everything. Since the constant is really a constant, K1 and K2, therefore, what relationship were we testing again? Go up there again. Point charge, right? Oh, therefore, this relationship is valid and the sphere follows inverse. Not to say lah. The sphere behaves like a point charge. How about that? Okay, so how about sphere behaves like a point charge because the relationship is based on a point charge. V 1 over X, this thing is point charge from what we learned in the previous unit. So now, still follow the same relationship. Okay, so behave as point charge. So there's 3 marks here. The first one comes if you know this idea that Vx should be a constant. Everywhere on the graph, V times X should be the same value. And also, you did 2 values of K your method. Like paper 3, hashtag AS paper 3. Then you said some kind of conclusion that makes sense and our examiner can understand, can get A1 mark already lah. Okay, so therefore K1, K2, therefore behave like point charge. Because point charge relationship is V proportional to 1 over X. Okay, pretty cool, interesting twist of a question here. Next, assuming that the charge does behave like a point charge, it does, we already proved it lah. Use the data from the graph to determine the charge on the sphere. Charge on the sphere is Q. Just now we already write the equation. So V equals to KQ over R. Or we can expand it a little bit. V equals to 1 over 4 pi E naught. Epsilon naught. I keep saying E naught. Q over, instead of R, they use X here. So it's good to follow that as well. See the axis down here? X. So let's do that. X. So we need to calculate our value of X. Let's plug in some points. So what point should we choose? We have to choose some point on the graph. Use data from figure, they say. For convenience sake, I'm just going to pick the old point that I already choose down here. 0.09 and 20. I'm just going to choose the same point to save me some time. So I'm going to use that point to calculate the charge on the sphere. Let's keep that peekaboo in the corner there so I can see that. So the V is 20 volt. I think it's 20, right? Yeah, 20 volts. Plug in. 1 over 4 pi E naught times Q. I don't know what is Q. I'm trying to find Q. X is 0.09. Or square or not? Square, no square. Make sure you know which one is which, okay? So, side note, what is E naught? Reminder, where to write? E naught is a constant you can find in your calculator or at the first page of every exam paper. That's 8.85 times 10 to the negative 12. So, press calculator and rearrange to get Q. You get a pretty good number, about 2.0018. Okay lah, 2.002. Okay lah, sure. Times 10 to the negative 10. Okay, so final answer, I guess I could pick 1 or 2 SF since my least is a 1 SF. Sure, 1 or 2 is fine, but I like 2. So I'm going to do 2.0 times 10, negative 10. 2 marks. Okay lah, this one not too bad lah. You need to know how to choose your points. So M1 here, if you plug in stuff into the equation. And also final mark 2.0. There we go. Not too bad. So this is how you can make sure you know. It's an interesting skill on the top right? So use your charges. Remember how to think of inside the sphere, outside the sphere, why it behaves like a point charge. All this reasoning, you got to be able to explain it. Next one, or next 2 questions are beautiful graph questions. Lots of graph questions. Let's start with this one first. This is ON15 P43 Q5. Go check out the question if you haven't, because this one also have to think a bit one. So we have a positively charged metal sphere. Ooh, when they say sphere, it's not a point charge anymore. No. The electric field strength is measured. Now it's an E graph from the center of the sphere. X of the field is shown. Okay, so looks pretty standard, I think, this graph. If I drew it out, it will look something like this. So you have a sphere. You measure from the center to some don't know where lah. So this is the axis lor. If I draw like that, this is X. Okay, so what is the charge? Positive charge. Okay, might as well draw some positive charge on the sphere. What is the first question that they want us to do? Suggest why for values less than 4, the electric field strength is 0. Where is 4? Here. Why suddenly electric field strength dropped to 0? Remember, inside the sphere. So you need to describe you are inside the sphere, but how do you get all your 2 marks? So they say, why is it 0? Don't just say because it is inside the sphere. No. You need to explain the physics why it is inside the sphere. So here's how you can talk about it, like what we looked at in the theory video. So inside the sphere, you can talk about how the charges are distributed. So if you draw something like this, the charge will distribute very nicely on the surface. They will arrange themselves until there's no more net electric force or electric field, and then they will still stay there and don't move anymore. So inside the sphere, charges, I will add on are evenly distributed, but this one you don't need to mention for marks. So charges are evenly distributed on the surface of this charged conducting metal sphere and are not moving. That's the very important one. They are not moving already. They have arranged themselves in a certain way so that they are not moving anymore. And what does that mean? Hence, there is no net force on these charges, which tells me what? Oh, because F equals to QE. No force means no electric field. So, no electric field. Okay, so if you're wondering why is it that, you remember a bit if you have an electric field, let's say like this shape, if you put a charge here, positive charge, it will move It will move either this way or this way. But if the charges are not moving, that means there is no electric field. Somehow everything has cancelled out beautifully and all the charges just chill there, nothing to do. So this is how you must describe it for your 2 marks. Okay, let's see. 1 mark comes from this part when you say inside the sphere charges are not moving. That's 1 mark there. Then you say, oh, because of that, no net force, no electric field. Don't just say, oh, because you're inside the sphere. No, you must explain the physics behind that. Okay, next. Point charge move from 7 cm to 5 cm. Okay, looks like we have to use the graph. Use the figure. There we go. Use the figure means look at the graph to get your answer. To estimate. Oh, this is an interesting word. Estimate the change in electric potential energy for this point charge. Electric potential energy is U, delta U. But this is a graph of E. How on earth are we supposed to find U? How are they related? This is the part where you gotta think a little bit. How is electric field and electric potential energy related? Look back at your notes. Look back at the theory section from before. Okay, but the idea is this. If you want to find U, but you're at E, so the only thing we know about U is that you have to go through a certain part to get there. You cannot directly just calculate electric potential energy. You have to either go find other things. So for example, if you know force, F equals to QE, if you can find the force, then you can find the change in electric potential energy by integrating the force with respect to how far you travel. Okay, go look back at the summary picture, okay, the 4 pillars of electric field. With this idea of how to find brain hang. Okay, never mind. We say can integrate, right? Integrate means find area, but this is a force graph. What we have is an E graph. Look, E graph. So let's sub in some stuff to make sure we can do that. So if I want to find change in potential energy over a certain distance from x1 to x2, this will be QE because F equals to QE I sub inside here. So dx. Yay, so I can integrate now. So this one will be Q integrate of E dx. Now this part means area under the curve. Whenever you see integral, it means area under the EX curve. So integral of EX will be from how many cm? 7 cm to 5 cm. So you are moving from, where is 7 cm? 5, 6, 7. Here is 7. Move all the way to 5 cm. So that means what is the area under this part? There. If you can find this area, you can solve this problem. How to find, miss? Count the boxes. If they give you a graph paper, probably you have to count the boxes. So you make your eyes zoom in a bit and count the boxes. Cannot, you can calculate here is kind of a rectangle, maybe a little bit more. But I just count 1, 2, 3, 4, 5, 6. Count, and I got roughly estimated a value of 0.76. So my area is 0.76. Yours will be a little bit different. That's okay. You just have a slightly different answer Don't worry, this one got a range of answer. So you count you figure whatever way you want, you estimate this area of this shaded region. That will be what you will use in your calculation down there. So I got 0.76. What did you get? Never mind, just continue on. So let's write out our working here. So we do know that, I'm just going to ignore the negative sign because we just want to change in energy. So here we know it will be Q times the area under the EX curve. Wow. We do that already, lor. So that will mean, what's Q? Did they give to us? Got this one here. So the point charge, Q is for the point charge going closer to this sphere. So this will be 8.5 times 10, -9. Check and see your calculation. Area under the curve, I got 0. What's my one? 7.6. My estimation. Estimation means I sure got a range of answers 0.76. Okay, so if I multiply that, I should get a value of about 6.46 times 10 to the -9 joules. Very small change in energy. Now you may check the masking and say, Miss, my answer is different, your answer is different, all the masking is different. It's okay, don't worry. If you're using this area method, they have a generous range of possible answers they allow. So this is 3 marks, right? The first mark is if you know how to get to this conclusion. U equals to Q times area under the curve. Okay, then the second mark is they will see what area you use here. Okay, so this mark is for this. And they generally allow 0.77 plus minus 0.07. So this is okay. So which means if you are somewhere 0.7, you estimated somewhere between this range, 0.7 to 0.4, you are okay and you can get that mark. Okay, so it's very big range. You just count the box, estimate, whatever formula you want to use, okay? And lastly, of course, the final answer mark is whatever you get down there, 6.4, 6.5, 6.3. So if me, then I'll just write 6.5 lor. If I estimate a bit smaller, then I'll write 6.3 lor. Whatever I can round off to, okay? So etc, 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 following through whatever you got for the second part. Now, if you're wondering, Miss, how they know this one plus minus 0.07? There's a trick how you can check your answer. If you don't like this method, you feel like, I don't like counting boxes, you could integrate if you know how to do it. So some people may want to integrate the equation down here. So if you do it the maths way and do integration, you would get 0.77 as your answer lah, which is, I guess, the most precise one. You need to calculate Q and you can do that. So I wouldn't recommend you do the integration here. Only 3 marks lah, no need to do. But if you're very free, you have extra time, you want to check your answer, sure, go ahead, integrate. So go check out the mark scheme. There are at least, I think, 2 more methods inside there, but I recommend thinking about the area one. You can go and try figure out if you understand what the mark scheme is talking about in the other 2 methods. Okay, so remember, how do all 4 quantities relate? Force, field, electric potential energy. 4 things. Then you know how to move between all 4 of them. Okay, last part for this section of examples. This one is my favorite. You know why? Sketch graph, 3 marks. Sketch graph, 3 marks. End of question. Well, at least for this part lah. Wow, 6 marks there just to sketch a graph. If you don't want, I want. So let's see. Wow, how to sketch? What is this? MJ16 P41 on the same page as the previous, I guess. 19 for this version. Still looking at spheres. Okay. A solid metal sphere is isolated in space. Again, when you see sphere, underline the sphere. That means you are looking at not the point charge anymore. You're looking at a sphere like this. What charge is this? Positive charge. Okay, so you draw lor, positive charge distributed on the surface of the sphere. It should be a 3D diagram. But anyway, you get the idea. So this one is looking at what's happening at the surface. So at the surface, you have a certain potential V, field strength E. Field strength get weaker and weaker the further away you go. So these dotted lines show how the electric field look like. So E is getting weaker as you go further away. But if you want to draw potential, I'm going to use purple. At the surface is Vs. Then as you go further away, the potential get lower. So V is lower as you go further away. Okay, so how are we going to draw the variation of electric potential with distance from the center of the sphere? Oh, must draw everywhere. From the center. So from this dot right in the middle, all the way out to some distance, I don't know, x. These are axes lah, 0 to x. How to draw? Where to start? Let's start from inside of the sphere. That's the easiest one. So I'm going to plot some points, key points. The one we know for sure is the surface. At the surface, you have Vs. So surface is what? R lah. Because here is radius ma. So here is R lor. Yeah, I draw the R there. Okay. At the surface R, you have Vs. So let's put a little x. At surface, you have Vx. Like that. Put an X mark there. Or put a dot, whatever marker, as long as you help you draw a better curve. Okay. Then what to do? It's easier to look inside the sphere first. So this at the surface. Inside is here. What's the potential inside? Constant. Constant potential inside there. So good to know electric field, nothing. So inside there you must draw a constant straight line like this. Okay. Then what happen outside? Then that is where the inverse square, all those things appear lah. So you draw something like that. Don't draw like this. Make sure you plot points because this is 3 marks. So you need to think about the relationship between V and X. What's the equation again? V equals to KQ over R, right? So that means V is proportional to 1 over R. And this is what we need to check. So at the surface, Vs is R. So if you go a little further, say for example, we need to draw until 3R. What do we do? Every R lah. Okay, we do every R. So if I want to move to 2R, I'm showing you my shortcut how I deal with ratios. So I don't have to calculate every single thing. So this is 2R. That means this will be 1/2 of the original, because the ratio is the same. Okay, good to know. Let's plot this point now. 2R should be 0.5 VS. Somewhere here. Next, what if you want to go a bit more further and go to 3R? So I'll write here 3R. That means it will be 1/3 of my original potential. So 1/3 is what? 0.3, is it? My brain suddenly hang. Yes, 0.333333. So you need to find where is 0.3333. I think it is somewhere. Let's see, this is 0.2. Nah. 24283233, somewhere here. Okay, now at least I know more where to draw. You can add more points, but I think this is good enough. So you try your best to make a nice curve, lor. Draw nicer than me, okay? Nice smooth curve, if you can, on paper. This one 3 marks, oh. You know where it come from or not? First mark, your inside sphere correct or not? Straight line, constant. Yes, correct. Second part, this section correct or not? Smooth curve from this point to this point. I don't know why they section off, but I guess they want to give you more marks. If it's smooth and it's a curve, 1 more mark. Last one, if it's smooth and it's a curve for this section, correct. 3 marks. Wow, very happy. Okay, so know how to draw the potential curve. This is the V curve. Next curve they ask you to draw is the other one, a E curve now. Oh, let me copy and paste the diagram first. Simplified version now. Okay, so we need to do the same thing. We start off best at the surface of the sphere itself. So we are looking at what we're doing now. Electric field strength. Oh, so maybe it's good to make a note. At the surface is ES. And at the surface, what's the distance? R lor, because center is 0 ma. So here must be R. So let's do the first point now. At R, you should be at ES. Inside the sphere, got electric field or not? No, just now we already say an example. So inside the sphere, you should draw nothing. Well, draw something down here. Sorry, not nothing. No electric field, but you draw a line down there. Make sure it's thick so that you can see on the paper. Take a ruler lah, okay? On your paper, you draw darker a bit. Then after that, it's also an inverse square, but do not just do this. You will lose all the marks. The marking is very specific. Go and check it out. So once again, think about the relationship. E equals to what? KQ over R square, right? Right? That's the equation. But for this, well, E field strength is E lah. So E is proportional to 1 over X squared. Wow, inverse square law. So you do the inverse square relationship. Oh. You know that at the surface, ES, the distance will be R. So this is R law. R square. Change it to X. Since we use X here. Then if you go a little further, do the ratio thing, or you can do my shortcut. This one be careful. The whole R here is changing. So that means I have to do this. If I go to 2R, what's the ratio or factor of my electric field compared to the surface? 1/2 square is what? 1/4 lor. Don't forget the square. So let's do the first point. At 2R, it should be 0.25 already. Wow, dropped so much. Yeah lor, here is 2. Where is 2.5? 2.4? 2.5? Somewhere here. So make a little mark or X for that. And the last one, since we can do one more, so we go ES 1 over R square. What is the R, the new R? New R is 3 times away from the center. So that will be 1/3 square, so 1/9. 1/9 is, by the way, 0.111. So you have to find at 3R where is 0.111. 0.4.812, somewhere here. Check your graph properly. And then, okay, I'm sweating already. How to draw a curve? Try your best to draw a nice curve that joins all these points together. There, I think this is my best attempt. I tried to know how many times already. Okay, so 3 marks again, as you can guess. Inside, if it's 0, correct, 1 mark. Then between the R and 2R, if it's a smooth curve, decreasing, curving like that, decreasing with decreasing gradient, okay, correct. The third one here, between the 2 points, correct. Okay, so they actually check the points, so it's good to do all this calculation to see exactly where it will pass, at least for each R, when they ask this kind of thing. If you get all 3 marks, 3 marks here, 3 marks here, done. Okay, so this is the whole first section on the main ideas of how you can apply your understanding about spheres, inside the sphere, outside the sphere. How do you deal with all that things? So go check out the next 2 examples, standalone example questions that look at more weird stuff based on these ideas. But that's all for this example video. Hopefully that was helpful. Go try out and check through some of these again to brain it a little bit more. That's all for this example video. See you in the next one.